Hi, this is Brian Powers. Today we're going to look at StatCrunch and the tools that it has for doing one sample hypothesis testing on a population proportion or on a population mean. So we'll be looking at, for the population proportion, the a z distribution or a standard normal distribution, and the tools for doing hypothesis testing first. So when you do hypothesis testing, the classical method involves calculating some test statistic from your data, and then also calculating a critical region or a rejection region, and determining whether your test statistic is in the rejection region or not. If it's in the rejection region, then you reject the null hypothesis, and that's the procedure. So when you're doing that, you need to, from a significance level, say in this problem alpha 0.025, we want to get a critical region for a right-tailed test. This is going to be done using the normal probability calculator. Remember, since this is a z-value, we're using a standard normal distribution. And so I'm going to this is a right-tailed test. A right-tailed test means we want this rejection region to be in the right tail. So we want to check this greater than or equal to. And we want that a level of probability in that tail to be 0.025. So this is what we're talking about. The cutoff for 0.025 in that tail is 1.959. Let's round it up to 1.96. So in this case, if we were to do a hypothesis test, calculate a test statistic, which would be a z statistic in this case, if it was greater than 1.96, if it was anywhere in this red region, we would have sufficient evidence to reject the null hypothesis. Okay, using the p-value approach, we have a hypothesis test to do. The null hypothesis is that the population proportion is 0.4. The alternative is that the population proportion is greater than 0.4. We have a sample size of 250. We have a sample count, a frequency of 110. That's 110 people from the survey said yes to whatever arbitrary survey question we asked. And the alpha level of 0.01 is the decider for whether or not to reject this null hypothesis. If we calculate a p-value, if it's less than the significance level, that means we have sufficient evidence to reject the null hypothesis in favor of this particular alternative hypothesis, that the proportion is greater than 0.4. So we have to do a couple checks to see if we have conditions met for doing a hypothesis test. These are conditions for whether or not the central limit theorem applies. So the first check is whether our sample size is big enough. Is the sample size, that's 250, I'll put this here, is the sample size times the proportion from the null hypothesis, 0.4 times 1 minus 0.4, is that greater than or equal to 10? Yes, indeed it is. That's a good check. Now, the other check would be if the sample size isn't too big, but that's really not a realistic concern in many cases, so, and it's certainly not in this case. For a sample size of 250, we're going to assume the population is huge, and so that 250 doesn't come close to being too big of a sample size, such that our samples would no longer be independent of each other. So let's find this p-value. Under the stat menu in StatCrunch, we're going to go for proportion stats, one sample proportion stats with summary. And here we're going to set the number of successes was 110. That's our sample frequency out of 250. And we're going to perform a hypothesis test. P equal to 0.4, that's our null hypothesis, p greater than 0.4. So that's it. You just set that up and you click compute. And what we're going to get here, I'll make this a little bigger so we can see it all. We are given the p-value. We're given a standard error of our estimate of 0.44, a standard error, the z-statistic 1.29, and the p-value. So all we need here is the p-value. So let's just copy it in with 3 decimal places, 0.0984. Now, is that p-value less than my alpha level? Nope, it is not. We fail to reject. We do not reject the null hypothesis because the p-value is greater than alpha. That's how we make our conclusion for using the p-value approach. Using the classical and p-value approach. Okay. So going back to StatCrunch, open up for proportion stats, one sample with summary. I'm going to set my number of successes to be 100, let's see, we have 78 out of this sample of 150. We have our null hypothesis 0.55, the alternative less than 0.55, and now I'm going to click compute. This is going to give me some of the information, but this doesn't give me the critical value. This doesn't give me the critical value for rejecting using the classical approach. For that, I need to go back to the stat menu, go to my normal calculator, and since this is a left-tailed test, because the alternative hypothesis has p less than 0.55, I want my red tail in the left, and I'm going to I want that left tail to be 0.10. That's the level of probability. That's my alpha level. Hit enter. So this tells me my critical value is negative 1.28. I'm going to take my hypothesis test results and bring it right above. So I have a z-statistic negative 0.7385, and I have a cutoff of negative 1.28. So I have to ask myself, would this z-stat fall into the rejection region? And my answer is no, it would not. It's going to be somewhere around here. So I would fail to reject the null hypothesis. I do not reject the null hypothesis. Now, from the p-value approach, I just simply compare my p-value of 0.23 to my alpha level of 0.10. And because the p-value is greater than alpha, let's just type it in, 0.2301. Because the p-value is greater than the alpha, I do not reject the null hypothesis. So you're going to have the same conclusion whether you use the classical approach or the p-value approach. So let's see, we want to find some critical values for doing a t-test. So going back to StatCrunch, for the t-distribution, I'm going to look up the t-calculator under calculators, the t-distribution. So for these, we have to set the degrees of freedom, and I have to set the fix the tail to be the right way. So the first one, I'm looking at the critical value for a right-tailed test for a population mean at alpha 0.05 with 10 degrees of freedom. So degrees of freedom is set to 10 coincidentally by default, but I want to do a right-tailed test, so I click this to be greater than or equal to, and now I'm going to set my alpha level. What was it? 0.05. Okay, so just correct that here and hit enter, and I get my cutoff. This is great. 3 decimal places, I'm going to take 1.812 and bring it in here. My t critical value is equal to positive 1.812 for the right-tailed test. Now, for part B, I want to do a left-tailed test, so let's just change that first. Left-tailed test, less than or equal to, alpha level of 0.10, so let's just correct that to 0.10. and I'm told I have a sample size of 15. That is not my degrees of freedom, that's the sample size. For these one sample population mean tests, the degrees of freedom is 1 less than the sample size. 15 minus 1, 14. That's what I want. Set my alpha, set everything, and I got it. So I'm going to take, again, 3 decimal places, but I'm going to put the negative sign in the first pull down. Negative 1.345. And here now I've got a two-tailed test with alpha at 0.10. So and with a sample size of 11. So let's get it all in. So we've got two-tailed. For two-tailed, I have to go to the between calculator. I set my now I want the probability out in the tails to be 0.10. The only way to get that with the t calculator is to use the complementary probability. That means I want 0.90 in between. And my sample size of 11 tells me the degrees of freedom is going to be 10. You click compute and you're going to get your cutoffs. This is great. So it's 1.8125. That's 1.813. This requires me to put plus or minus 1.813. I don't know why it wanted it at 812. That's not right. Okay, great. So now we want to do a hypothesis test. Let's go back to StatCrunch and pull up our hypothesis test. For t-stats, we're going to do one sample with summary data. So I'm told I have a null hypothesis mu equals 100, alternative mu not equal to 100. Let's put that in right now. Mu equals 100 is my null, mu not equal to 100 for my alternative. My sample mean is given here, let's see, 105.3, 105.3. My sample standard deviation 8.9, and my sample size is up here 20. So put that in, click compute. This is going to give me my output. This gives me the t-statistic and the p-value, so you can do it using, you can make your conclusion by the classical or the p-value approach. It's asking for the t-statistic. Let's bring it in with 3 decimal places, 2.663. And now let's see, what would a critical value be with a level, alpha level of 0.01? Remember what we just did? We want to do find the cutoffs for a sample size of 20, as in this problem. We would have 19 degrees of freedom. We're going to have, at alpha level of 0.01, that means we're going to have a probability of 0.99 in between. Click compute, and we're going to get cutoffs that leave 1% split between the two tails, 2.86. So this is asking for the 2 critical values. I'm going to put them in negative 2.80, let's see, 861 and positive 2.861. And what does this picture look like? Now remember, what the picture I got over here is the critical region is the white part, not the red part. So what I want is this. This is what a two-tailed critical region looks like. So we want to compare now. What if my test statistic was 2.663? Would that be out in the tails? No, it would not. This is between those two cutoffs. It would be in the red on this graph over here, which is the do not reject region. So there is not sufficient evidence to reject the null, since the test statistic is between the critical values. There we go. All right, a golf association requires golf balls have a diameter that is 1.68 inches. To determine if golf balls conform to the standards, a random sample of golf balls was selected. Their diameter are shown in the table. Let's take a look at this table data. Okay, so we have 12 golf balls measured. Let's bring this into StatCrunch where we can actually work with it. Bring this smaller. Okay. Because the sample size is small, the engineer must verify that the diameter is normally distributed and the sample does not contain any outliers. The normal probability plot and box plot are shown below. Let's look at those to answer this first problem. This is a normal probability plot and a box plot. Now the box plot doesn't indicate any outliers. It's a skewed distribution for sure, but whether or not there's anything that is going to cause us alarm, in the normal probability plot, all of the data points are within the bands here. Let's just say this is fine as far. I would say that the conditions are fine. There's no reason to assume the distribution it's coming from is not normal, so let's just say yes, that's fine. What we want to do is do this hypothesis test. Do the golf balls conform to the standards? Conduct a hypothesis test using the p-value approach. So the null hypothesis is that the population mean equals 1.68. The alternative is that the golf balls, the mean width, does not equal 1.68. If it's higher or lower, that means they doesn't conform to the standards. So that's why we're choosing a two-tailed test for this problem. Let's get a test statistic. So let's move over to StatCrunch, and under the stat menu, we'll do a t-stat, one sample with data. We have the data in our column, and we want to do a hypothesis test. Let's just set the null 1.68 versus not equal to 1.68. And that's it. Click compute, and we get our info. We have a t-stat of 0.808. Take 2 decimal places, that's 0.81. And the p-value, it's right here, 0.436. Do we reject at an alpha level of 0.01? Well, clearly, the p-value is higher than that. So whenever the p-value is greater than your alpha level, we do not reject. So there is not sufficient evidence to conclude the golf balls do not conform. This evidence is inconclusive. We can't reject the null hypothesis. So for now on, we still have to assume that these golf balls are in conformity with the standards. That's that. A math teacher claims she has developed a review course that increases the scores of students on the math portion of a college entrance exam. Based on data from the administrator of the exam, scores are normally distributed. With a mu of 523, the teacher obtains a random sample of 2,000 students, puts them through the review class, and finds the mean math score of those 2,000 students is 528, with a standard deviation of 116. All right, so the null hypothesis would be that the mean remains at 523, just the same as the regular population. The alternative would be that the score has been increased from 523 to something bigger. To test at an alpha level of 0.10, okay, we want to do a hypothesis test. Let's go back here. Let's do a new hypothesis test, t-stat with a one sample with summary data. The sample mean was 528 as stated in the problem, the sample standard deviation of 116, the sample size of 2,000. The null hypothesis was that the mu was equal to 523, and the alternative is that it increased from 523. And let's compute. Well, we get a t-stat of 1.927. 2 decimal places, that would be 1.93. The p-value, 0.027. is the sample mean statistically significantly higher? Again, we checking whether this p-value is less than the alpha level. P-value of 0.027, alpha level of 0.10, that p-value is less. That means we say there, yes, there is statistically significant evidence that the mean is higher than the population mean from that null hypothesis. So, although we can be statistically confident, or there's statistically significant evidence that this teacher's review course does improve math scores, raising the mean from 523 to 528 probably is not very important. So this is an example of when something can be statistically significant, although not practically important. So significance and importance aren't the same thing. All right, so now let's take another sample. Let's edit our hypothesis test. I'm going to move things over a tad. So now suppose our sample mean is still 528. The sample standard deviation is still 116, but suppose the sample size was 375 instead, smaller sample size. Now let's see what the results from the hypothesis test would be. So now the test statistic is 0.83, and the p-value is 0.202. Is the mean statistically significantly higher? No, it's not anymore. The p-value is greater than our alpha level. Remember, our alpha level is 0.10, so that's not less than that. It's not significantly higher in the statistical sense. So what would we conclude? As the sample size increases, let's see, the likelihood of rejecting the null hypothesis will increase. However, large samples tend to overemphasize practically insignificant differences. That's another way of saying unimportant. Okay, great. So that's how we can do hypothesis tests in StatCrunch. I hope you enjoyed, and I hope this helps.